and welcome to the official Debrief podcast. My name is Michael Mataluni, and I'm thrilled today to have Dr. Abel Mendez here. He's a planetary astrobiologist and director of the Planetary Habitability Laboratory. The Hab Lab is a research and educational virtual lab studying the habitable universe from Arecibo, Puerto Rico. Welcome.
Yeah, hi, Michael. My pleasure to be here. And the issue with the habitable word, there's issues to pronounce that English and in Spanish. It happens to me too. So it's very confusing, though.
Well, I appreciate you bearing with me. So can you tell us a little bit about the Planetary Habitability Laboratory and your work there, how you came there, what it is?
Yes, we started 10 years ago, our Habitability Laboratory at the University of Puerto Rico, Arecibo. This is a campus of the UPR system. There are 11 campuses, and it's about 30 minutes from the Arecibo Observatory. So that's the only connection, that we are close to the Arecibo Observatory. But as part of my research, which mostly in this lab, theoretical research, that's the thing that I love. I also do observational things using the Arecibo Observatory. And our lab is dedicated mostly to understand habitable place in the universe. So from a point of view of theory, we start by looking at Earth today and through time. So that's our reference point. Then we go and try to understand a few interesting places in the solar system. And then going beyond to exoplanets, planets around other stars.
Fantastic. So it sounds like you're doing a lot of work from the lab, and you're using Arecibo as are you theoretically coming up with ideas in the lab, and then you're testing those at Arecibo, or like how are the two connected?
Yes, Arecibo for us is our telescope was for using and measuring stars with red dwarf stars. So that's the connection to habitability. These red dwarf stars, many of those have potentially habitable planets. And the only thing that, because we were not able to see anything at all with Arecibo for the planets, but at least to the star, studying the star,
Right.
the activity of the star, flares, so we can measure how good or bad are these stars for the planets. So from the theoretical work, we know that, and we established in 2011 the first catalog of potentially habitable worlds. That's one of the main projects of our lab. And we do theory to try to use theory from other scientists and our theory, just to determine what are the planets that match at least some of the conditions that we know are required for life. And when we do the observation at Arecibo, guess what? We pick those stars that are with planets that are mostly interested. But the issue is that we were not able to see all the sky. So Arecibo was limited to some strip from the sky, a big strip. So we have about 5 or 6 targets that we know have potentially habitable, but there are more.
Right, absolutely. And so what is the current catalog of exoplanets that we believe could be habitable?
Yeah, we divide the catalog into potential possibilities. If you want to be optimistic, there are up to 60 potentially habitable planets. So far, of over 4,000 planets that are known.
So of 4,000 that you've been able to observe, is that what you're saying?
No, that we know that has been discovered.
Ah, got it.
By telescopes around the world. So telescope on the road since the 1992, which was the first one was discovered in the Arecibo Observatory by coincidence. So telescopes around the world up to today have been discovering exoplanets, and we know about 4,000, more than 4,000 exoplanets. But out of those, only 60, if you want to be optimistic.
That's still pretty good. That's like 15%. I mean, that's not so bad.
So if you want to be more realistic, then maybe it's just 24.
Okay.
because on those samples there are many big ones, maybe more than 1.5 Earth radius. And when that happens, that planet might be something else, like a water world or even a sub-Neptune, a small
Right.
Neptune world. And too much gas, that's not good.
Right.
And
Right. But it also
so
depends on what we expect to see from life, right? Because isn't it possible that we could see traces of helium, which would actually could potentially promote life, but maybe not the same kind of life forms we are?
well, for reference, we take life as we know it. And for searching, we search everything.
Okay.
So, for example, that's one of my main problems to establish from a terrestrial point of view, thinking about life on Earth is limits. And, play a little bit with those limits, to anticipate anything new.
Right.
Then see if we detect something and that we might recognize as life. So some weird guesses that we were not expecting, and we were asking, is this life or not? Then our models could be used to say, okay, no, this is something that we don't expect from a terrestrial sample. So if this is life as we don't know it. So
Right.
the only way to recognize life as we know it is using our standard.
Right.
Otherwise, we won't say is this something that we know of. So that's why it's important. But people are
Right.
looking for anything at all.
Right. And there's a difference between looking for life and looking for a habitable planet, right? Which is
Yeah.
the focus of your study.
Yes. I'm not that interested in actually discovering life, but all the habitable places. And the biggest question that I am very intrigued more than finding life is finding a planet that we consider habitable by our standard, but there is no life at all. That's
Right.
profound, because the mantra here is if the place is habitable, then it should have life. But that
Right.
requires that the life started already. And probably for exoplanets, that will be something hard to know if we ever detect some gases related to life, or if we ever could be confident that there's life is detected. But the key here is probably just Mars. It's next door. Because imagine that in the near future, maybe 10, 20 years, we excavate the near surface of Mars and we find
Yes.
running water. And we analyze by our standards and we see this place is habitable.
Right.
If we put terrestrial life there, it will thrive. But we don't find life. That
Right.
will be amazing. Even right, we're not transferred between the Mars and Earth at some point in the past. There's no independent origin for life. That will be, for me, that will be more amazing. I know already a planet with life,
Right.
and a habitable planet with life. I don't know a habitable planet without life. That's
Right.
for me, it's more intriguing for me.
Yeah, that's an interesting paradox that I hadn't considered before about how profound that would be. What are your thoughts on things like the Fermi paradox? And if you're saying that being conservative, maybe we found 20 out of 4,000 or more that are potentially habitable, which just the sheer amount of stars and potential habitable planets in the galaxy. What are your thoughts on the Fermi paradox?
Well, I think let's put it that we are alone.
You
We
do.
are alone by not because there is not life elsewhere, but probably because it is too far away.
Okay.
So technically alone for practical purposes. And the issues here, we have Earth as an example. So we have at least one point of data. And so this is a real problem that scientists have to study, that we know that the universe can have habitable worlds with life and even intelligent life. We are the sample. So we are not looking at anything strange, and you're not asking for square planets or something that we have never seen before. We are looking for things we already know they exist.
Right.
Problem is another one. It's just the problem. Another case, which is not believing all the planets that are in the universe. by estimates. And then it's like logical to say, well, there should be another planets like us. Okay. But when you study this field in particular, and this is probably the easiest assumption when you are trying to learn this problem, but the more you study, and I mean astronomy and biology, and see how hard is to life to evolve from microbial life to complex life to eventually intelligent life, how the planet evolves and has to keep the same a good environment through billions of years to keep that life going. You see so many obstacles that probably what is abundant is planet with life, but eventually something in the planet, it became too hot, too cold, and then it's gone. So that's probably what happened with Venus and Mars. So we have two examples here. So the planet went wrong. Probably they were right at the beginning, but no, Earth is the only one to survive.
Right. So you're talking about extinction level events on a complete scale, like wiping out all of life.
Yeah, for many reasons. In terms of the planet, impact, radiation, explosion, supernova, whatever's close nearby. So there are many things that could go wrong in terms of destroying life.
Right.
So probably that kind of planet with had life, microbial life for a long time, are very common. And maybe nearby, and one of the 20 planets, 24 planets that we consider now potentially habitable, maybe that's the case. But then to have all the conditions, and when you try to think all the conditions, you study this field in detail, you see that, wow, that's a big step for complex life or even intelligent life. So we should be a few. If you put a few in a big galaxy, randomly, they will be far apart.
Right.
Too far probably to know each other. And that's what I'm thinking, that to solve that Fermi paradox is not that there shouldn't be any intelligent life. It's that we are just too far away from each other, so practically isolated and alone.
Right. When you would need some sort of faster than light travel in order for it to be even feasible, right? Or it would just take forever. What do you think of Avi Loeb's assertion about Oumuamua? What are your thoughts on his hypothesis?
Well, I like the idea that when you have a interesting hypothesis like this, is a very interesting hypothesis. So for Oumuamua, and to people at the beginning thought that because of the size of this body and its behavior and being an asteroid instead of a comet, then people started to speculate. But Avi then took and wrote a paper about that, a scientific paper, which I read curiously about the details, because it's good always to have a mentality to recognize one thing from the other. I don't want to, we try to not make mistakes, something natural, something artificial. I mean, artificial rendered like Earth, something terrestrial. Or even alien. So we need to recognize, and we train for that. And but I read the paper, and I also read all the papers that explaining as a natural explanation, and I see that the best fit is a natural explanation. So of all the explanation, then you put the alien hypothesis in the bottom. For me, that's total bottom. It cannot go lower than that, because we have other more and a diversity of explanation. The problem is that we cannot be sure what is the final explanation, and we won't be able to do. But that's something that we have to consider. Well, the other issue is the media exposure and media attention of what particular hypothesis. That's other issue. But at least in terms of the hypothesis, we have to consider all the hypotheses, and then just weigh them according to. So for me, it's just a natural object.
Right. So you're saying that there were some strange behaviors with Oumuamua that created this opportunity for this hypothesis. There are other natural explanations, but those natural explanations are purely theoretical, and we don't have the data to make that decision. And from your scientific perspective, you kind of prioritize it on a certain levels, right?
Yes, yes. I don't even have to go through all the details of this hypothesis, because the first thing I will say is, okay, this is the first interstellar object that we detect. So a piece from another solar system. And if in my mind, if we ever detect some piece like this, first I will think it will be a comet, because they are farther away from the stellar system. They are less bound by gravity. They are more likely to go free and something composed of ice. But no, it was not like that. It was not composed of ice. So that's interesting. So it's a rock. So, okay, so the next best thing I will say, okay, if it's a comet, then it will be an asteroid, a rock, more composed of rock, because they are abundant in the system. And you're telling me that the first thing that we see is just an alien piece of machinery instead of a normal rock, which should be more abundant, no matter how many civilizations and the trash that they put in the stellars between stars. There will be more trash of asteroids and natural things. So I will expect those to be more common. But fortunately, about 1 year after that, we detected a second object, Borisov, which is a comet, as expected.
Right.
And then so without looking at hypothesis, that's your first scenario. It will be more likely because these fragments from planet for stars should be more common than any alien device. Right. But then when you look at all the hypotheses in detail, trying to explain the particular observation, you see that it is just a natural object.
Yeah, I mean, I found the natural explanations to be very theoretical, because we've never seen any of the explanations from those theories either. We've never actually seen those. So I definitely it really got me thinking, because of the one that was most compelling to me was the non-gravitational force that was exposed on it. Like, that was really the most interesting thing to me. And then the light variations, which were just, but that still could be an elongated object, a very flat object. There are plenty of possible explanations. We just haven't seen these things before.
Yes. Well, at least the jet, we have seen those jets from comets, but the reality is that usually we see some gas too when we see those jets. So probably these jets were much less powerful and more probably randomly, as far as it was exposed to the light on the sun. Eventually, it just puff just sporadically, and they're only very interesting idea that is probably nitrogen as a nitrogen body, and nitrogen is usually gas everywhere. It's very hard to make it solid, but this is some object traveling through space, and it was part of the comet, and it had water and it had nitrogen. Probably water went because of the heat, got away. The nitrogen was too hard, very solid. And then this is something in nitrogen, and I find that explanation, wow, that's amazing. I prefer that explanation than aliens. I was, wow, as I said before, I seen planet with life. But with a asteroid composed of pure nitrogen and solid rock, wow, that's amazing.
Certainly would be, right?
Yeah.
Let me ask you this: let's talk about Arecibo for a second, and the methodology for searching for exoplanets. Can you kind of describe to me the transit method, the wobble method, and other ways that you're currently using to discover habitable planets?
Okay, so scientists in general are using different methods to detect these planets around the star. So most of the methods, see, we try to summarize what other scientists are trying to do to detect these planets, are just by looking at the star, how the planet affect the star by passing in front of the star, which is the transit method, by perturbing the orbit, which is the wall method, by also through time the star is moving and the motion of the planet, eventually the trajectory of the star that it makes in the sky will be, that's astrometry. So basically, these are the methods we detect these planets. Once in a while, because if the planet is big, is hot, and is far away from the star, we literally see the planet. So those are the less cases. So most of these planets are like we haven't seen each one directly, only indirectly by the effects on the star. Right. So that's why the method. But the one discovered at Arecibo was the wall method. But this planet was altering the pulsation of a pulsar star, which is very periodic. And we noticed changes in this period of the star. And those periods, what was the explanation of this change in the period? And when you model, if consider of all the possibilities, let's assume there is a planets there, and what planet size and what distance will explain that. And then you have a wonderful fit for the data and what you see and you model, and then you realize, okay, this is definitely a planet around a pulsar star. But as I said before, I am not going through any detection method. I'm not trying to detect a planet. Only when the planets are detected, I look at them to the stars with Arecibo, or from the data, try to understand the theory on what we might expect. One of the things I try to calculate, estimate this surface temperatures, because we don't know that. We only know, in summary, what we know of the planets is their orbit and their size.
Right.
And when I say size, I mean the radius or mass. Sometimes both, but sometimes just one or the other, depending on the method that was to detect. So size and orbit, that's it. So there's many questions there. Okay, I want surface, I want atmosphere, I want details. And those details we go in the next decade. So the last decade, since 2010, that we have been discovering this Earth-sized planet in the habitable zone. We have been detecting them. Now it's moving to not only detection, also characterization. And the first thing that we will be able to characterize is their atmosphere. We have done this before for big planets, but I mean now for small planets. So we will be able to see the atmosphere of this planet until the composition, at least some important gases like water, carbon dioxide, oxygen, we might be able to detect in this decade and the next.
What sort of technology are you using to detect those things?
Okay, for detecting gases in the atmosphere, there are two ways you can do it. Right now, the easiest way is because if the planet was detected by the transit method, so it needs a planet to be transiting. When it passes in front of the star, the atmosphere of the planet, of course, is passing through the star. And you know the light of the star without the planet and without the atmosphere. And now you have a reduction of the intensity, but you also passing through that light of the star or the original light through the atmosphere. And there will be some absorption depending on the gases that you have there. If it's, for example, clouds, which are usually white and block any light at all, then you will notice what compounds are. So that's a big deal when we have planets that are at the top, they have a cloud layer. So the light didn't pass through too much atmosphere because cloud block almost all type of light, at least visible light.
Right.
And but depending on less clouds, then that you might have a strong signal enough to see different composition. And you have also this is a problem on a spectroscopy that we know from all time in astronomy. We do that with stars before we do the experiments in the lab, and we see these phenomena. So we can catalogize different type of signal depending on different elements. And then from that information,
when you say signal, is it colors? Like what exactly is the spectroscope looking at? Like what kind of data are you pulling from that?
Okay, that's quite easy. If you have the signal of the star, that will be the intensity of light, the
Okay.
intensity of light at different frequencies, at different energies, then will be colors. So this is like the signal of the star. Let's say a straight line, at least in the frequencies you are looking. And you will see a dip in intensity. A dip in intensity at different frequencies. And we know, oh, at this frequency, we know that oxygen absorbs light. So it's intensity what you are looking, but that intensity is in terms of frequency now. So it's like a color spectrum,
Right.
but it's more broad because it's not only visible light. It also includes light in the ultraviolet, in the infrared, especially in the infrared. There are many elements that absorb in the infrared. So we see that dips in the intensity of the light compared to the original light from the star, because the star, depending on composition, will have some dips also. That's how we know the composition of stars.
Right. That's absolutely fascinating. That's the best explanation I've ever had. I've been trying to wrap my head around this for a good minute, and it's very, very challenging, but I completely understand that. I appreciate you breaking that down for me. Let me ask you this. Are you familiar with a two-tiered approach to assessing habitability of exoplanets?
Okay, so are you talking about the Planetary Habitability Index and the Earth Similarity Index to approach? We wrote that paper in 2011.
Okay.
That was one of us. So I was curious, okay, why you wrote that up?
Yes, because, exactly.
Yes, okay. So
I was setting you up.
Okay. So in 2011 we wrote a paper and suggested two approach to understand the habitability of the planets. One was a planetary habitability index, and that index required more information about the planet than we know, about how much water it has. But at least in theory, is something that we can use at least for understand what will be the limits depending on what we expect on the planet. But I also work in that paper, and in my work in that paper was with the Earth Similarity Index. And the Earth Similarity Index is not a habitable index, it's a similarity index, it's a comparison. So you pick a set of properties and compare those properties with that of a base of comparison, in this case, Earth. So that's what a Earth Similarity Index. So this was a straightforward approach to things we do in computer science and other areas. Similarity index. For example, for face recognition, you establish some pattern, and then if you are looking at that object and image that pattern, then it's similar to, and it will recognize that face. It's also using chemistry to recognize chemical compounds. It's also using biology to compare diversity. You have different populations of different organisms, how you compare them. And so it's used. So I saw that, and I thought, we have now a zoo right now of exoplanets. So for sort out what exoplanets are more similar in terms of those variables, and we did in that paper a comparison with some variables, including surface temperature, which we don't know for exoplanet right now, but we at least we can model and sample the parameter space there. And but the idea is to show that this approach, depending on what you have in the planets, you can compare them. So hopefully in the far future, we will be talking about more about this kind of Earth Similarity Index, traveling through space, through stars, and looking at the data, and then say a signal, and it will combine, and it will be so much data for the user that give me a summary of what that. Okay, the Earth similarity is 0.9. Okay, that's not that. Okay, it's getting similar to Earth, and that, okay, this is more interesting. This is closer. Okay, let me go into detail the data. So that's the idea of this similarity. So the idea is combining similarities with habitability index. And that's something that we might put, because, for example, there could be planets that, like planets around M-dwarf stars. And those planets could be similar to Earth, say, in terms of size and the amount of light. But in terms of habitability, could be something else.
Right.
So not necessary all the planets that look like Earth might be habitable like Earth. And that
Right.
is the point.
Just because they're in the habitable zone, you're saying that you've got to cross-reference different indices in order to understand habitability, as opposed to just saying, well, it's pretty close to the sun.
Yeah. That's something that we learn from biology on these habitability models, how they apply, which
Right.
I see that people tend to believe like this is some magic that you can do until is a planet is habitable or not. It's not like that. It doesn't work like that in biology. It's more like a library of weighting different parameters and how those parameters, the ones you choose because they are easy to measure or or easy to work with, and how those parameters compound to the habitability of the system, make the
Right.
system more better or not. And then at the end you will have like a library. You're looking at a stellar system. You have different metrics. It's telling different things, and depending, okay, if you are looking something more like Earth, this, but if you're looking more like habitable in terms of the surface, or maybe it's in the subsurface you are considering. So different. So it's a compound problem of many indices. That's the goal. And then you make a decision on what you want to do with that information. Okay, which one are you gonna see first? Which methods you will design to detect that, to confirm any of these metrics? So then, or in the future, which one you will go to travel to?
Right. I love how passionate you are about this. I mean, this really, you can tell it's your life's work, and how deeply motivated and inspired you are by it. And from a layman's perspective, I think it's so valuable to understand the work that you do in order to really respect the complexities that are behind this, and understanding how we can really understand. Because as a layman, you hear from the community, and then you see this beautiful picture of new super Earth discovered, and they show this lush, beautiful planet in this image, and you're just like, oh my God, that's amazing. But the complexities are so much deeper than that.
Yeah, people think that because we have this catalog potentially habitable world, we are very positive about planets
Right.
with life. It turns out it makes it worse everything, because you know so much, and that I see those planets and I think about, wow, maybe they are none at all are habitable as we believe. So that's a big deal, that we don't know enough information about this planet, and at least we know they are there. That's a starting point.
Right.
I remember as a kid thinking about other countries, and so I am here, and there are other countries, and people are doing different things, and I see that on TV, and I'm missing that information, missing to see that personally, and that's strange. But then I learned about Mars, and there is a big place, and something happened on Mars, even wind or sounds that I hope to get soon. more. So, and that's happening, and we are missing that. And now there are planets, and I don't care if they're habitable or not, but we are missing what is going on in this planet.
Right.
There are places, and we see the solar system, how amazing it is, all the planets and the moons, and how different each one are. So we have a lot of surprises waiting for us in the cosmos.
That's beautiful. And I love your passion, regardless of whether or not we find actual life, but the fact that we don't know what we're going to find. And when we do find it, regardless of whether it's habitable or has life, it's still going to be pretty freaking amazing.
Yes. Either answer is amazing. But as I said before, I will be more amazed for not finding life. That will be, oh
Right.
wow. So this is how special we are. So that's
Yeah.
why I like to do this, because it's not that at the beginning I was more interested in searching for a different life form, and more I was intrigued. But the more I learned, that was not anymore the main focus. It's us. It's us understanding other places, or habitable or not. Let us understand our evolution as a planet, and then detecting even life that tells something. Okay, we are not that special. Okay, that was expected. but not finding life. Whoa, wow, we're that special. That's a big thing to know.
Yeah,
Either way.
that would be extraordinary. If we were the only forms of life, it just doesn't. It boggles the mind to contemplate. What do you? I'm really excited about the new Mars rover Perseverance. I'm really excited about the caching system and the search for extremophiles and other single microbial organisms, remnants of those. Do you anticipate, like, what's your gut feeling? Do you think we're going to find it? You think we're going to find life in these caches?
Oh, wow. I think it will be very hard to tell from the observation through the mission if this is something real life. We have a drill for that in 1996 with the Martian meteorite, and we have the meteorite in our labs. Right. And it took years for people thinking about analyzing this meteorite just to say, okay, this is just a natural process and not life. So it confuses us. And that's amazing, even having the sample. So I doubt now, by that experience, that even together is, and for particular microbial life, even having all those instruments just to tell from afar that, okay, we detected life. It has to be so obvious that if microbial life is not obvious. And so I think that the best thing is to get the samples back. Once we get that samples back, I think we might get something positive or not, which will be amazed is something not positive. And I mean, this is for will be life in the past. So the Mars was habitable, we think, in the early days, because they had a liquid water, and we see now all the ingredients necessary, just the missing liquid water. And
When you
so
say the ingredients, so when you say the ingredients necessary, what do you mean exactly?
Okay, so in the composition of the on the soil, well, one way to see it, which I love to explain it like this, is when people ask me how we can determine if a place is habitable or not. Okay, we can simplify that by follow the water, and you see that mantra using NASA. It's more like follow the classical elements. And what the classical elements? So you need air, you need water, you need earth, and you need fire. Well, more technically, you need an atmosphere, which provides some gases necessary for life. You need water, and this water, but it could be other liquids. And then you need earth, and you mean the rock, because not all elements necessary for life are in a single phase. Not all are, at least the 5 elements that constitute the DNA. They are some in the atmosphere, some in the water, and some in the rock. So you cannot have life in the rock phase or the liquid phase alone, or gas. And then the fire is the energy, is the symbol for energy, solar energy, chemical energy. So in Mars, the particular problem right now is the water. Is the water was it has to be liquid. It doesn't. Solid is not good. It has to be liquid. The atmosphere has a few things instead, like carbon dioxide, which is important. There is in the rock all basic elements like iron, sulfur, phosphorus, so all those elements there. And then we have the energy from the sun. It's still now, and it was like that in time. So so the missing ingredient here is water, and we see from the rivers, and probably even had a small ocean in the northern hemisphere. So we see that the water was present a long time ago. So as a first approximation, this was a habitable place. And now Perseverance has the duty just to find that any signs of that past life. And even life, microbial life, alive now is hard to detect in small quantities. Then, and you're trying to do for the past environment, so fossilized life, so remainings of life, telltales that life was present, and that will be challenging, even taking the samples back on Earth.
Right. Right. So you think even if we get those samples back, it's going to be very difficult to identify fossilized single-celled organisms. But it's possible, right?
Yes, it's possible. Yes, definitely. It's possible. Yeah, we thought with the Mars meteorite, we thought we had that. Right. Actually, all the evidence, when you look at that, you will definitely be convinced. Oh, that's life. That's life. That's the easy approach.
What changed? What did we recognize or understand that made us go, oh, we were so wrong about this?
Well, there were 4 evidence of life there. So the idea is taking these 4 independent evidence for life in a single structure there. Then you say this is tantalizing evidence for life. And the strongest of those evidence, one was morphology, the form, but that's the weakest one. The strongest one was the magnetite crystals in the sample. And the shape of those magnetite crystals, which magnetite crystals occur everywhere. But biology tend to make those magnetotactic bacteria try to make those crystals in one particular shapes. And when we look at that, the shape just match how microbial life does that on Earth. And we don't know of any natural process to do that. So that was the best evidence. The last one to go down, because eventually somebody in the laboratory was able to naturally, in an environmental setup, produce those shape of crystals. And now we are like, okay, it is possible to produce that. So you can still say that, and some people believe still that there's a good evidence there. So you can say, but it's not that it's a good evidence. Fine. But now you have the doubt, because you can make those ingredients naturally occurring in that sample. So you have doubt.
Okay, so it's still good evidence, but it's not incontrovertible anymore. Like we thought, this is absolutely it, and then now we go, okay, it is possible that these crystals could be made in a very natural way that does not require life or biological.
Yes, and natural environments are more common than life. So.
Right. As we know, right.
Yeah.
Let's talk a little bit about Arecibo. In November, our own MJ Benias here at the Debrief reported about the collapse and pending demolition of Arecibo. However, Puerto Rico pledged $8 million to start the rebuild. Is that are they following through on that? Are we seeing the potential for this to happen?
Yeah, the government of Puerto Rico is very interested in keeping the Arecibo Observatory together. And now, and I have to clarify, the Arecibo Observatory is still working there. The facilities is only the main telescope, because there are there's a small telescope, there are other things, other experiments that they're doing. But so it's only the big telescope missing. And the government of Puerto Rico wants to keep the observatory running, and with a big telescope again. So they they just want to give all the support necessary, logistic support, to make it so, and even money for at least that money will be to one of the things is that the way to go to the observatory, the road now is taking the heat of many trucks coming in and out, because they are removing material. So that is not included in what NSF will be fixing. They're taking charge of cleaning everything. So what else they need money for? So that could be something. But also the design, because once we start in this proposal and we wrote a white paper that was published in early February, and the NSF will see that, and they will like it or not. They may decide, okay, let's go forward with this. But they will have to ask Congress for approving that money. It's not something that we expect the NSF to provide that money. So big instruments need that input. But one of the questions...
Oh, sorry, go ahead.
But one of the questions that will probably the Congress and NSF will have is, Puerto Rico is eager and he wants to keep doing this and he wants the observatory. So there is a big yes from the government and even money that's telling you, okay, we has already started the design
Right.
of the telescope. Even that design might not be the final one because it will take some time and then approval and then revisions but the ball is running at least but still that funding has to go through. So we are still
Right.
dealing with that.
Right. Are there any other funding methods underway that can help support Arecibo?
Well, there are other ideas, but I think because NS is a property of the National Science Foundation, it's a federal facility.
Okay.
Then any other idea they have to be approved by them because they are the owner of the land and the facilities.
Oh, so people can't just contribute or donate. Like if somebody listening to this is like, wants to bankroll you guys, they can't.
Well, the observatory can do that. The observatory,
Okay.
the facility can do that because they need to fix many things, and people have been doing that, and they have the donation page.
Okay.
But for taking over and constructing a new facility, then even if you have all the money and show you, okay, we have all the money, okay. Well, probably that what they say, okay, this was a science facility, and we want to keep it like that. So no matter how much money you are putting, and want to make sure that it will be used for what they want to do for science. If you want to make a recreational park and give you money and give me all the land, that's no go. So it will have to go through NSF and their decision, and then so that's the best approach, and then to Congress. And if that fails, then we probably be more creative. Like,
Right.
okay, maybe it was not approved in general. Maybe the Department of Defense, if they want have some idea how to use that area, at least, and keep the science, then maybe they have a lot of funding more than any agency. So probably they could take it. There's people thinking ideas like that. Or then maybe if everything fails, then we would try to go forward with something else, like consortium or universities or institutions. But NSF have to release the facility, have to agree on anything because they own right now the land and everything there.
Right. I understand. China's release, or they're finishing their FAST telescope and releasing it to foreign governments. Is that something that is a similar type of telescope to Arecibo?
Yes, is the China FAST telescope is a 500 meters telescope. Arecibo was 300 meters. So it was a little bit bigger and a little bit sensitive, in more sensitive, at least in some frequencies. But Arecibo had a wider capabilities on frequency, so it was still more sensitive in other, let's say, type of light that you can see in the universe. But the most amazing thing about Arecibo was the radar. So it was able to actually not only listen, but also to emit radio waves and to send a signal. That's why in 1974, the famous Arecibo message was sent from Arecibo. You cannot ask China to do that right now.
Right.
He's not the radar too. And that radar capability was efficiently used for monitoring asteroids, including some asteroids that might be hazardous to us.
Okay.
And that's something very important and for life on Earth in the future. And we don't have that now. We don't have that capability now. It was the most powerful radar in the world. And the other radars are much less powerful. So we lost something big that was not available elsewhere.
Is there anything that you'd like to be working in the lab that you're not now? What's the future look like for Hab Lab?
Okay, so we plan to do many things, and we want to create better models of habitable planets. We want to keep using the next generation Arecibo telescope, which is what the name we are already putting for the. It will take probably 3, 5 years, or even 10 years to construct a new. Is an amazing facility. One thing that we were planning to do, starting on August, which we did observations 4 days before the first cable broke. So we have to stop the observation. So I had students that we were trying to do something else with Arecibo, because we, as I told you, we were monitoring this red dwarf star that we know they have potentially habitable planets. Just monitoring the star to see how bad or good the star is. But we are getting everything from the star and the planet. So any radio emission, and planets emit through a process with the aurora, they emit also radio, but they are very weak and usually out of the frequencies of Arecibo.
Right.
So for that, you need other telescopes. But we're getting everything because we are looking at a very wide frequency range. So we thought, why not doing 10 signatures? The SETI project is not optimize our observations for SETI, but at least I had one student that was planned to continue doing the observation of the stars, but also, as one third of her time was to, okay, let's try to see something there, because we are looking at the prime candidates for habitable worlds, and to see, and it's important. And I told to the student, okay, don't get very excited. I don't expect them to find anything. These are indoor stars, and indoor stars are very bad. But at least you can tell me for sure that there's nothing there. At least if with this intensity and this frequency, there is no transmission. This is very important to know that something is there that is not there. And in this decade, and the next decade, when we detect biosignature for exoplanets, if we ever do that and see that there is a life process going, like oxygen, okay, so there is life, but that could be microbial life, that could be complex, intelligent life. So the next question by people and the scientists, if we detect that kind of life, say, is that intelligent? And we won't say, oh, we don't know because we haven't searched the signatures. That's something that we don't do. And wait, you have to do that. So that's why I think this decade, biosignature and technosignature is something good. If you detect something like a biological process there, and then you see through technosignature, there is nothing, at least you know now you have context. There's nothing like Earth right now with intelligent life there. So that's important to know. So that planet's probably less evolved or whatever. And that's quite important. Not to say we don't know. So that's why it is important to you to try that.
No, that's so important. And I really appreciate you bringing that up, because so much of what maybe the layman thinks about science is that the overspecialization is just insane. And the when you're asking a question in one domain of academia versus another domain, maybe those things aren't talking to each other. But the fact that you're looking at this from a holistic perspective and saying, no, we have these different technologies, we should be using them to try to get a more full picture. I find that pretty amazing.
Yeah, we try to be creative with our data. So anyway, we were planning to do new observation, but we have 3 years of observations already for many stars with planets. So the students are continue that work, and you will hear results from Arecibo for a long time. So probably you will scare what the goals of the telescope. No, because Arecibo has been keeping data since the early days. And that data, as astronomers have been using that data, archive data, for a long time. So that's very common. So we have data, we are still analyzing the data, and it will take some time to get through all the data. So you will see from many scientists new research from using the archive Arecibo data.
Right. I recently spoke to an astrobiologist. Her name is Tessa Fisher, and she was mentioning to me that they were using network theory to help locate life on other planets. Are you familiar with network theory?
Oh, I was a little bit familiar with that. Once we tried to use a method that could be related to AI or machine learning, I think the problem with those methods is data, which is the same problems I have. I have model from one perspective to say if the planet is habitable or not and compared to Earth, but we don't have data and we have enough data and we have to be creative about the possibility. That's what we
Right.
call explore the parameter space. What are the possibilities? Just to constrain what will be the limits.
Right.
And from that point, yes, that's really important. But we are having a hard time to figure out things.
Right. Is that something that a rebuilt Arecibo could perform if it's rebuilt and improvements are made?
Well, it took some times during December after the collapse just to getting together with all the scientists and collaborating in a white paper. And I am not an engineer, but I am scientist, and I know what we need to do. So my collaboration was, okay, I want the telescope to do this, because we can learn this, and that.
Yes.
And there are all of the different astronomers also requesting things.
Yeah.
So from those requests and the engineers got together, and I remember getting the final, well, the first version of the white paper and saw the design. I was totally overwhelmed. Okay, now I understand. In the 1963, when that Arecibo telescope started operating, it was a amazing structure out of science fiction because it was an incredible machine. And now when I saw that, okay, I felt like that. This is a science fiction, right? This is science fiction. We can build this. Well, it's amazing. Well, and it's now public in the Arecibo site. There's the complete white paper, and it's quite different that was before. Instead of just one dish, there are many multiple dishes, even maybe 1,000 connected in a plane, and they work together. That's a phase array. And phase array you can use also to scan the sky without moving the platform. So you will be able to scan the sky and also transmit in different directions very fast. But the plane will also, to increase also the perspective, it will move, and it will be a little bit bigger than the 300 meters. It is estimated 340 meters, a little bit bigger. And the sensitivity of that, when I look at the sensitivity, look at the detail sensitivity, it was the same as the China. So it was the same, but
Right.
a much broad frequency range. So
Ah.
something, well, all that frequency and the sky coverage, 2.5 larger, wider view. So you will see objects that we were not able to see before. And that sensitivity and that sky coverage just got me. So that's amazing. And there's also the radar. The radar was more powerful and different frequencies, but more powerful, which means that we will be able to sample objects farther away, like uh,
Right.
like interstellar asteroids that we detect, and we want to tell for sure the shape and not by estimates on light curves, but actually the shape and the picture. Yes, that's something that we do. Actually, Arecibo was in the detection limit for Oumuamua.
Really?
But yes, but why was not Arecibo used? Because that was in October 2017 that we discovered Oumuamua, and Arecibo and whole Puerto Rico have a Hurricane Maria in
Yes.
September by 1 month
Yes.
difference. So it was
Oh.
not able to do that. So what a coincidence of life that the only instrument that was capable, at least in theory, to get the actual shape of the object, actual picture from radio bounce, it was not operational because a hurricane. Because a
Oh
hurricane. Arecibo
my.
went back operational in radio for December. It took a few months and just sample another routine asteroid that was in the schedule. But that was totally bad luck. And now we don't have Arecibo. So we are totally bad luck right now for anything happen.
Right. Oh, that's brutal. We got it. We got to get this thing up and running.
Yeah.
Let me ask you this. Are there any other techniques or technologies people are using to search for habitable planets or extraterrestrial life that are kind of interesting, but you're not really that maybe are outside of the respectability of the scientific community?
Well, I don't know. Also, respectability. No, probably people will try to make, or some scientists might try to make fun of anything related to technosignatures. But as I told you before, if we are trying to detect life. These
Right.
exoplanet characterizations ideas is not only to detect atmosphere components, but also the possibility of life. So we are trying to detect life.
Right.
And that's why important to, if we ever detect that, and then those people won't be joking about, because probably they think that life and signature is the same thing, and we won't be able to do so. So I
Right.
don't think that we are the scientists in particular, most of them. We think the possibility of life from simple to complex is a real thing, and we have to look. That's the big deal. Even that the people like me that in this term I don't feel too hopeful, because I think they're too far away. But anyway, you have to do it, because it's important to know that that is not there something.
Right.
That tells something about us.
You need to be able to prove or disprove. One of our writers spoke to the folks at NASA running the James Webb Observatory programs, including a pair of research teams who one time on the telescope to search the TRAPPIST-1 system of exoplanets for atmospheric signs of life. Can you share with our listeners what TRAPPIST-1 is?
So the TRAPPIST-1 system is a planetary system of 7 planets. It should be called Snow White and the 7 planets. And that that system is about 40 light years away. And then all the planets in the system are all the same size of Earth. And 3 or 4 or up to 4 planets are in the habitable zone. And all of them, all of these planets transit. So you can see their atmosphere. And James Webb Space Telescope that will be launched later this year will have at least probably the capability to look out through this atmosphere and detect some interesting gases. One of the interesting gases is oxygen, and it's very unlikely that it will be able to detect oxygen. The signal will be too low for detection. But other gases, yes, like carbon dioxide, water, CO, and that will provide us with an idea of is there some biological process going in these planets. And the best thing, because there are other and even closer transiting planets, but they are not necessarily that close in the habitable zone, or they're just one planet or 2 planets, but you have all the context. And that's what I was telling you. It's important to know if a place are habitable or not, because it provides you context. And you will see the nearby planets, and you expect that those planets won't show atmosphere at all because they are too close. If you find atmosphere, okay, there's something wrong with theories. And then there's the farthest planet that is very cold, and you have to realize that some components of we should be available in the atmosphere and others not detectable. And then you have these planets in the habitable zone, and probably if you detect some, let's say if we are able to detect methane and oxygen together, that would be the best candidates. And together, not one or the other. Let's say we detect those in one planet, but not in the others, and the planet in the habitable zone. We will be, wow, celebrating that we probably detected some life process, at least microbial life, but planet-wide.
Right.
and in making those gases. But let's say we detect that in the planet, in the cold one, in the hot one. Oh, okay, there's something wrong here. Maybe about instrument measurement techniques. We don't know, or maybe if this is real, this we have to go back to the scrap board
Right.
because something is going here. So if if you just have one system, one planet, and detect biosignatures, you won't be that confident. So at least this system will provide some more confidence, we provide some context just to verify and compare each result from the planet. So that's why it's the best laboratory so far for exploring the idea of understanding the atmospheres of planets in different distance from the star,
Right.
plus the possibility of also understand life on those planets.
Oh man, that's so tantalizing. I'm sure that that just is an incredible opportunity for you and your work. Are there any other systems that you guys are looking at that are that good or similar?
And there are other systems transit the planet, but usually they are far away. And there we have a one of those potentially habitable planets is next door in the Proxima Centauri, which is 4 light years away, not 40 like Trappist.
Right.
But this planet is not transiting, so it doesn't got in front of the star. So you
Ah,
cannot tell from the current instruments, James Webb and others in this decade won't be able to tell the atmosphere. You need another instrument for that, which will take by the end of this decade or probably more to be built. And that's other telescope that will put a block in the light from the star. And for the first time, this planet that I told you has been detected by just the how they affect the star. We will see those planets as a dot because you have to block the light of the star. It's too bright. It just consumes the light of the planet. So if those telescopes will block the light, and so now you don't need the planet to be transiting because you will actually see a point of light from the light from the planet, and then you will analyze that light from the planet.
right.
And it's the same idea because the star have bring some light to the planet, but when the planet reflects light, it will absorb, insert frequencies, telling you about the composition. Now it's not
Right.
passing through, but it's by reflection. And you will able to tell from that information, even as the planet rotates, you will able probably to take to see land and oceans, not because you see the planet as a disk, but you still see a dot. But oceans are darker, much darker than land. So if you look at that planet for hours, days, it will probably go, the light reflected will go up and down, with a pattern that will match some model about land and continents ratio. So that's
Mm.
amazing. Now, from the atmosphere, you will learn that it has water vapor, and now you see that it has continents. And if your instrument gets better, probably will take 20 years or so. That instrument also, it will tell you the green from the plants. From all the reflected light, there is some absorption that could be attributed to chlorophyll, to a process similar if the planet is widely covered in vegetation. And that will be the final nail. But that, okay, not only we thought that this planet and this and those nearby will be not for with those instruments, those nearby will be the good ones. And that will be the final decision that this planet is not only habitable by our standard, but now we find is it actually has life.
Right.
So we will be able to do that probably in 20, 30 years, 40 years. We will have that capability. And people are asking about, wait, what about if we found that green? That means, but life on Earth, from experience, we know that we have epochs that our planet was green and there was animal life was starting to flourish. So that doesn't mean that there's animals there or even intelligent life. But we want to know
Right.
more.
Right.
People would like to know more. And that will take other instruments which might take a longer than that. This will be a network of telescopes, big, huge telescope, 10-kilometer telescope. For comparison, Arecibo is 300 meters, so it's not even a kilometer, half kilometer for the one in China. So 10-kilometer telescope, 100 kilometers telescope. These are massive structures. You don't have to build them in one piece. So actually, it's better to build in different pieces, scattered throughout the planet or even in space. And when you build those instruments, then you will have the capability of see the planet as a disk.
Right.
At the beginning with a blurry, but at the 100 kilometers could even see islands in the.
Wow.
But even that, you will see, unless that civilization have super large cities, more bigger than the cities, because even when a satellite picture of Earth from afar, you don't see the cities. It doesn't look like there's intelligent life. But unless that the planet has big cities, it's a super civilization, we won't see that and say, okay. But there is an alternative, because in nighttime, that planet should supposed to go dark, but it has cities like us. From a planet, you will see the light of the cities, that little bit shine from the light of the city, and you will take, oh, there is an civilization as advanced as us that is producing artificial light during the nighttime. If we see it dark, it means that there is no intelligent life, or they just want to keep to be dark during the nighttime.
Right. No electricity, no inventions just yet.
Yeah.
That's absolutely fascinating. Abel, it's been an absolute pleasure spending time with you. If people want to learn more about you or Arecibo, how can they find you?
Well, there's our webpage for our lab, phl.upr.edu. There's always our Twitter page for the lab, Planetary Hub Lab, or my Twitter page, which I constantly share news about astrobiology. So you see, from biology to astronomy, what's the relation? It's because there's some relation to astrobiology. So that's I share a lot of news.
Absolutely. And what's your Twitter page?
Prof. Abel Mendez.
Prof. Abel Mendez. Well, that's fantastic. I'm following you. You've been just amazing. And thank you so much for spending the time with us today. Thank you for sharing your passion and your talent with us, and just this amazing research and progress that you guys are making at the Hab Lab. And just thank you so much, and have a wonderful day.
Thank you. My pleasure. I enjoyed this. Bye-bye, Michael.
Bye, Abel. Thank you so much.